Hi everyone. I am presenting autocomplete element fields for SIGCHI 2020. Aggregate elements are ubiquitous in our daily lives and a variety of applications. Creating them have been a common task for artists and designers. These elements can be created in several ways. Manual creation can offer full artistic freedom, but it can require tedious manual workload to place and adjust these repetitive elements, especially for large outputs. It can also require sufficient technical or artistic expertise. Automatic computation can reduce manual workload and expertise barrier, but often lacks sufficient user control for individual styles. It also requires full input fields, which might not be easy to obtain, especially in 3D domains. To overcome the aforementioned issues, we develop an autocomplete system for interactive authoring of aggregate elements. We implemented our system as a plugin for Autodesk Maya, a popular 3D modeling tool. Like conventional painting interfaces, users can select aggregate elements from a palette and directly brush them on the output canvas. Meanwhile, our system analyzes what they have done so far and predict what they would do in the future. Users can accept these predictions to reduce manual work or ignore them to maintain full control. They can optionally tune additional parameters, such as brush radius, from a control panel. With our system, users can easily create a variety of element distributions, including isotropic and anisotropic shapes. They can even combine multiple entries from the element palette or create new entries for future use. Here, the user is experimenting with brushing and mixing multiple music symbols. Now let me talk about our approach. To handle elements with varying anisotropy and deformability, we represent each element by a set of weighted samples and graphs. To synthesize these elements, we need to compute three main aspects: their positions, orientations and scales. Now I will describe how to distribute, orient and resize elements. Our element distribution formulation is devised to optimize the spatial locations of the elements. It consists of three objectives. The sample distribution term evenly spaces the weighted element samples. However, for dense packing, this term alone might create a lot of overlaps among elements. The conflict check term aims to reduce such overlaps. The graph similarity term can maintain the element shapes during the optimization. Our element field formulation is devised to optimize the scales and orientations of the elements from sparse user inputs. It also consists of three objectives. The field alignment term aligns synthesized elements under user brushed strokes. The field continuity term smoothly orients each element with its nearby elements, especially in areas not explicitly specified by the users. The element rigidity term controls the rigidity or deformability of the element shapes. Based on our proposed formulations, our autocomplete system can respectively optimize all the element scales, orientations and distributions over the whole output domain according to user intention via an iterative process. Our system provides several brush operations and assistant commands that can enable users to freely add, replace, and erase brush strokes or directly delete multiple unwanted brush strokes. Users can choose preferable stroke sizes and set tunable parameters, such as the number of iterations, to design a variety of outputs without requiring significant manual labor and technical expertise. With our system, users can iterate their designs, starting from a small number of brush strokes for initial exploration. They can add or remove more strokes to change the results. Users can also fine-tune the outputs with additional manipulation, including scale and density from the control panel, to create spatially varying effects. As shown in this dolphin example, the users can specify the density and scale from the menu and brush the corresponding strokes. When they hit the autocomplete button, our system will generate the full results. The results will obey the user-specified element scales and densities with smooth variations across the entire output domain. Our system can also help users create outputs with toroidal boundary conditions for tiling applications, such as seamless 2D graphic background and 3D texture mapping. Here, the user can place several strokes and let our system autocomplete the full outputs and visualize the effects in 2x2 tiling. To sum up, I have presented an autocomplete system to help users create aggregate elements with different shapes, scales, orientations, and deformability over 2D and 3D domains. Our system combines the flexibility and control of interactive manual authoring with the speed and convenience of automatic optimization. For future work, our current system cannot completely avoid interpenetrating and floating elements. These can be reduced by incorporating a step of physics solver. The performance of our implementation can be improved by incorporating GPU computation. Our method considers only discrete elements, and we are investigating how to extend it for continuous structures as well. Finally, even though our current prototype is deployed for desktop, we envision it can be helpful for VR brushing, such as tilt brush or medium. Thank you for watching.